is you don't know what exactly it is or whom does it exactly belong. But without much thinking in such a case, you will really be able to tell, for example, the gender of the person. You can say if it's a male or a female. You can even say if it is a kid very accurately. These are pretty, very basic speaker profiles. And in our context, we wanted to estimate some of these physical traits from the speech. So we started looking at age and bodybuilding characteristics. So bodybuild in the sense of basic stuff like height, weight, etc. So that's the problem statement. You have somebody's speech recorded and you would like to find their age and height, for example. And why would, and also, of course, the gender is available. Again, gender classification systems are almost 100%. You can get to the gender of a person without any mistake. So, why do we get to this kind of informations? For example, this is very useful in targeted advertisement, what is known as so. For example, uh, there is Google which wanted to show you some advertisement. It will try to show you some advertisement. It can actually, I mean, I don't think it is doing it currently, but it can show you different advertisements if you are young or if you are old, if it can figure that out. So that's basically about figuring out age. Figuring out height, yes, it has some other applications. For example, forensic applications. This could be like you have a anonymous phone call or something. If you can figure out some bodybuilding characteristics, you can try to. I mean, not we as in we. The legal system can try to narrow down on number of suspects. So generally, these are having applications such as e-commerce in targeted advertisements or forensics. Of course, there are also this caller agent pairing in call centers where they would like to know, okay, which part is this person calling, so I can transfer his call to a person from the similar region. Or if you distinguish the age, you can try to figure out which age group people are giving you the most complaints, or is it a problem with a particular age group. For example, old people, are they facing any special difficulties with the products, etc. That's the major motivation behind looking at the speaker profiling task, to estimate these parameters from speech. Now, so there has been a lot of physical parameter estimation systems, mainly in age and height. There are a lot of them. Okay. However, when we started this work, most of those works were only in using English data. So mostly in height and age estimation only. Nobody had looked at other kinds of physical parameters. And most of them actually worked on longer duration utterance, something like 10 to 20 seconds of speech. For example, in forensic scenarios, this kind of speech is not guaranteed. And again, there is no point in telling that we can only work with monolingual. So we wanted to investigate speaker profiling from a multilingual point of view. And also, the state of the art system, for example, in height estimation, it needed a text dependent recording. It required a particular vowel to be pronounced, it required a certain other vowel to be present, and it needs to know where that vowel is. So, this kind of things are not practical, because if you are calling up a call center, or if you are looking at the anonymous call, you can't ask the person to tell a particular vowel or a particular sentence. This is not practical. So we wanted to explore a set of features that does not use the that does not restrict the texture text content of it. So, and we wanted to integrate all of them together into one point. So this was mainly our focus when we actually started the this particular project. So this is just a overall view. I think there is just for understanding. You get your input data, you do a pre-processing and feature extraction. And typically, if people are familiar with the speech, people do feature extraction on a frame by frame basis. You get either a 1 second phase data or a 2 second data or a 3 second data, depending on how fast you or slow or how long or short your sentence is. Now, once you have that sentence, you cut it down to very small segments. Each segment is something like a 25 millisecond. So that's you find some kind of a spectrum or a related feature from it. That is what I mean by the feature extraction in the third box from the left here. So you extract features for each of those small segments. They are called frames. So you get a frame level features. Now you get so many frames per each of the sentence that you speak. Somehow you need to put together all of them to have a representation for the entire sentence. That is known as the representation of the feature. Now once you have that, you can train some machine learning system to do the physical parameter estimation. So in our case, we used what is known as a support vector regression. It is a very similar technique to support vector machines. We will come into the details later. So, again, for anybody who worked on speech, they would have heard this term L frequency cepstral coefficients. So we also started with that set of features to start our exploration. This is the MFCC. For those who doesn't know about L frequency cepstral coefficients, it is those little segments of speech. You take the spectrum and you look at a scale which is similar to the resolution of our ear, and you try to take a log and a inverse DCT to compensate for some channel effects. But apart from that, it is basically the spectrum which is at a almost at a log scale at higher frequencies. That is similar to our hearing resolution of frequencies. So you extract these cepstral coefficients at each segment, and basically you take the derivative of that and second derivative of that to figure out how this varies across the neighboring frames. So you get around 60 features per each of those little 25 millisecond segments. Now, in order to find one particular feature across the entire sentence, we use what is known as a supervector. So what is a supervector? You try to, this is a little mathematically involved, but we will not try to go through the equations. I'll intuitively tell what it is. So you try to take the entire speech and you try to come up with the different kinds of spectra. Basically, you have lot of sounds in your input speech. So you have, for example, the sound A, the sound E, the sound U, or vowels like ch and s, and so many such things, right? So you try to model these different sounds, and the way to model that it is what is known as the Gaussian mixture model. But you model each of these components and you try to find what is the average spectrum of each of these different components in your input speech. So we have a 256 classes, and each class you try to find what is the average MFCC looking like in this particular sentence. So that is our feature. So it's basically, if you want to go through the equation, it's a Gaussian mixture model. Each of the model you can find a probability, and you multiply that probability with that particular feature vector, the MFCC feature vector, and you try to take an average across the entire sentence. That is what the input feature is. For those of you who are familiar with the speaker recognition, this is similar to what is called as I vectors or super vectors and things like this. So it's a very similar approach. So basically, we didn't want to do anything new here. We just wanted to take something like a speaker recognition approach and apply it to the here. Okay, so the second set of features, so that we tried, and we will come to that. That was the first set of features we tried. The second set of features is what we call as formants. Formants is a very special characteristics of human speech. So basically, what are the formants? They are basically the peaks of your spectra. The So each and every sound which you utter will have a different kinds of peaks, and then you also have a fundamental frequency, the something which is referred to as pitch often. So for example, we know that male speakers have a lower pitch and female speakers have a higher pitch, and then when you sing you will have to really sing sometimes in very high pitch or very low pitch. So there is this pitch also which we consider. So pitch is what I denote with f0 here, and there are other frequencies which are f1, f2, f3, f4. Those are local maxima of the spectra. Okay. Okay, so again, this frequencies will be again dependent on the particular sound. Basically, if you are into physics, you know that your vocal tract, that is your sound producing system, is like a tube, and it will have its own resonant frequencies. These frequencies are called formants. So these frequencies, how do we estimate? You can estimate it using what is called as there is a way to find an approximate peak, an approximate spectrum using what is written here, that is called as AR model. Basically, this is called a linear prediction, and that will give you this four frequencies. Now, this is only each of those speech segments will have this formant frequencies. Now, how do we calculate the overall values for a particular sentence? We try to look at their averages, min values, max values, what is the median, etc. So those are called percentiles. Okay. So percentiles are, like, let's say, the median of all the values. That is called as 50th percentile. So what is going to be the 50th percentile is you order all the values from smallest to highest to find what is in the middle. Similarly, you can also find what is the smallest, biggest, what is the 5% percentile, 10% percentile, etc. So those are called percentiles. So we represent the whole thing using percentiles. The next set of things is what is called as harmonics. Okay, I should have talked about this first and then gone to formants. Nevertheless, it's okay. So, what is this picture, first of all? This is the picture of a sentence. Somebody saying one of these standard English sentences. Now, I told you about little segments of the speech. You take as input speech and you cut it into 25 millisecond duration segments. So each of these vertical strip is actually a spectrum of the sentence. So you plot the spectrum. So as you change the sound, your spectrum changes. That's what you see in the picture, the left top picture here. So you are reading some sentence. So around point 0.8, I have marked a window. That is one particular sound. I think it's a ah or something. So at that point, if you cut it, you will see if you take the vertical cross section at that marked point, you will get the picture on the top right. So you see that there are too many peaks there. Those are known as the harmonics. This is coming because your vocal folds are vibrating when you speak. Your vocal folds are what is there in your throat. So basically, when you speak, you can touch your throat and you can feel that there is a vibration. So these are known as harmonics, and it has been observed that they actually carry some information about the speakers. So we decided to explore these things also in addition to formants. So anyway, so these little lines horizontally are the ones that correspond to the harmonics. So you won't be able to see a lot of them. In fact, they are there all the way up to high frequency, but we will not be able to distinguish too many of them. As you can see from the right side top, you can only distinguish them until maybe 3000 to 4000 hertz. Beyond that, they are very difficult. So these two pictures, the top and bottom, actually correspond to two different speakers telling the same sentence. Okay, and these two marked parts in the left pictures, they are actually the exactly same sound. Okay, so you can note from the right side that in the first speaker, actually, who is a short speaker, actually has this gap between the harmonics as 230 hertz, which is actually high. And when you have a higher, sorry, when you have a shorter speaker, this is a taller speaker, sorry, the first one has a first one is a short speaker, the second one is a taller person who actually has a smaller gap between the harmonics. I think that is a known fact. You have a larger vocal fold here, so it has a lower frequency of vibration, and this is a smaller vocal fold giving a high frequency vibration. It's not about that. It's also there are other things how stable these frequencies are. For example, that is actually shown to have some correlation with the age of the person. If you are very young and healthy, your harmonics will be very sharp. These resonances will be very sharp. But as you grow old, there will be lot of variability happening in the harmonics. So since our aim was in general to do speaker profiling, we thought this will be useful in, for example, age estimation. Okay. So we wanted to see how these frequencies vary and how those relative amplitudes vary. So we those also we are considering as features. So we tried to look at these peaks and try to look at their median and likewise averages across the sentences, and we use them as features for the speaker profiling task. So any questions so far? These are the three different set of features that we used. First is the conventional MFCC features. Second is the Formant features, and third is the harmonic features. So you might ask me what is the formants, right? So for those who are not familiar with formants, formants are these high density regions. So there is a formant which is around here, which keeps going low, and then it goes high, and then it goes low again. It merges with the first formant around the point 7. Then the second formant shift, and it goes like this. So that's the formant. It's a high energy region. It's a peak of, if you smooth the spectrum vertically, so in the right side, if I talk, if you smooth like this, so there is a peak here, that's a formant, and there is a peak here, that's a formant, and likewise. So there is a last peak here around 7,000. It goes down here and it comes up around 7,000 and then goes down. So that around little bit around this region, there will be the last formant. Here it is more visible. There is a formant here, there is a formant here, formant here, formant here. The first formant is around 500 or 600 hertz. Okay, so that's a formant. Harmonic is this. So harmonics and formants are both the peaks. Harmonics are this very closely spaced individual peaks. Formants are the peaks in a approximate smooth spectrum. That is the difference between harmonics and formants. Okay, so we will continue with whatever we did. So we started our experiments with the pretty famous old timid data set. They had around 600 speakers, used around 450 to train, and another 170 speakers for testing. So we had around 10 speakers for, 10 utterances per speaker. So we had something like 1600 test samples to predict height and age. Now, before we go into results, I wanted to tell you about two more things. One is about the evaluation metrics. We can't estimate accuracy like in the case of classification task. For example, you can say, okay, you are predicting, let's say, images of cat and dog. If a cat is predicted as cat, you will count it as correct and otherwise incorrect. There is nothing like correct and incorrect, right? Because you have a height which needs to be predicted like 1.87 meter, and if you predict 1.77, we don't know whether it is correct or not, but we know that the error is 0.1. So that's what we are trying to see. We are trying to see what is the error that incurs in this prediction. Now, if you have to average the error across a large data set, you can basically square the error, add them up, and take the square root and see what is the root mean square. So that's one particular evaluation matrix. And often people also do this mean absolute error. Instead of finding the mean of the error, if you do, there are positive errors and negative errors. They can cancel. They just take the absolute value and find the absolute mean. So that's the mean absolute error and root mean square error. Those are the two evaluation metrics that we use. The other thing which I wanted to tell you is about the target mean predictor. So when do we say that this machine learning algorithm is working? For example, let's say you have a cat versus dog classification. Now, when do we think that this is working? You can evaluate it and you can say, I got 60% accuracy. Is it working? Now, we need to compare with what is known as the default predictor. So, if you default, let's say you predict every time randomly. So, if you have two sets to be classified to, let's say cat versus dog, if you randomly predict things 50% of the times you may be right. So that 50% is your default predictor. Similarly, we need to have an idea about what is the default mean absolute error or default root mean square error that we can get. So we take this as predicting the test samples by predicting simply the mean of the training data. Let's say I wanted to predict somebody's age. I just find the mean of the age in the training data and predict that number. that is known as the mean predictor. So it's so the we are trying to look at how much error do we get without using the speech data. Remember, this is about predicting the height slash age from the mean of the from the speech, right? So we need to see without using speech how much we can get and how much on top that we are able to reduce by using all these machine learning methods. So those are the two things which I wanted to emphasize. So so these are different things. So the first bar is basically the default mean prediction, target mean prediction. So this is giving, so this is the first two pictures on the left is about predicting the height. So you see that predicting the height, this uh, the first bar here is about MFCC based features. This is Formants. This is harmonic using only frequencies, harmonic using amplitudes also. So basically, you have a frequency. You can use its frequency or the amplitude or both. So you see that many times some of these features are not really getting better than the target, this mean prediction. But this MSCC based features, for example, was always getting better than the TMB. And similarly, 4 months also, even though it is marginally getting better, it was getting better than this. Harmonics was not getting better, especially in case of male height prediction. This was a very, very challenging place where we found that this was failing. Otherwise, I think every other case, these features, whatever we have tried as worked and given a number which is less than the default prediction. This is just the numbers, and we tried to then combine these individual outputs to get uh, better than each of these predictions. So basically we tried to do an average across different feature predictions. So this is some set of results that we have. So, and one more thing which I wanted to emphasize is predicting everything together is very easy, because once you predict some number for females and some other number for males, it is going to be a easy task. So you see that here the numbers reported are very easy as compared to the TMB. It is much lower than the TMB. But really, when the challenging task is if you were to only predict for male or female speakers separately. So these two are the real test. This is just here because we wanted to compare with this particular first reference, which is a very weak predictor. Okay. So you can see that in male set, we actually got close to the state of the, this was the state of the art when we started the research. We got close to the state of the art, but not really very good at it. But age, I think we got really better with both the male and female in terms of mean absolute error. Only this RMSE error, this was inferior, and that is because of a couple of speakers who was very high values. Right? This, in general, we were looking much better with our set of feature combinations here. So that's basically the feature combination setup. So we also tried to look at how these errors vary across different height values. So we divided the speakers into different height values and tried to see how much error we get in each bin. So we see that so this is the number of training speakers that we have, and so we had a lot of training speakers between 170 to 190. And so we see that in those two different places, the mean absolute error that we get is really small. It is around 4.7, 2.9, etc. Even the RMS error is very small. But when you don't have enough speakers, like here we only had 10 speakers or 30 speakers, for very small, very short people and very tall people, we didn't have a lot of data in the training set. And you see that as a result in the evaluation, the RMSE error of those two segments are really high. Same thing is happening with female speakers also. In the middle, where we had a lot of speakers, so they are actually pretty small. The ends, we have a very high RMS error. Especially this has only three speakers, and this is around 14, around 15 RMS error. Now, by the way, this is all in centimeters. I mean, when I say 2.5 is the mean absolute error, it's a mean absolute error of 2.5 centimeters. Okay, this is not meters, right? Okay, and similarly in age also. But in age, what had happened is we had more speakers across different age groups. So around 20 to something like almost till 40, we had a lot of speakers. Then it became 10, 13, etc. So it became less in the last region. So in male speakers, you will see that until 40, the age estimation errors are small. Okay, this is slightly high, the last one, but otherwise, these are 1.8, 2.94, etc. So this is relatively small. So therefore, the age estimation errors are small all the way from 20 to 40 years old test data samples. It becomes pretty high after that. This is like a 35-year-old RMS error. I mean, this is in years again. So 35 years is a huge RMS error. And it is because of this our overall RMS error is high. And female speakers, again, most of the female speakers were below 35. Okay, and therefore this is only small in the reach vicinity of below 35 speakers. That's about the duration. We also experimented with how much speech do we need to actually get to the numbers that we have. So this is also to evaluate the robustness of our algorithm if we have very less speech. This is very relevant, for example, for forensic analysis. You will have only 3 seconds of speech, or you will have only 2 seconds of speech, which somebody has left. And the question is, how good is the performance of the algorithm? So here in the x-axis, it is basically the amount of speech in seconds which is available, and y-axis is the MAE. So if you have very less speech, you will have a higher MAE, and which could be when you reach zero, it will be same. The dotted line denotes the mean prediction. So in the zero case, it will be as bad as the zero prediction. So here you will see that it is still fairly robust after around 2 seconds. This is pretty flat. You already get this performance which we talked about after 2 seconds of speech, which is one something which is good with the system, because we will be able to get some idea about the person if we have at least 2 to 3 seconds of the speech. Whereas this female speakers, maybe this we are assuming that this is because there are less number of female speakers. The trend is you still need almost 3 4 seconds of speech to get to the full performance of the system. So far we talked about limited data set, and we said around 2 to 3 seconds of data we can get reasonable to state of the art results in height and age estimation. Now, to look at the goals that we had, we need to look at multilingual data and multi-axon data, and we wanted to look at other physical parameters which is based on height, shoulder size, etc. So we collected a data set which we call it as audio forensic data set, and we had another project with the Indian Institute of Science, and we had a multilingual multi-accent speaker profiling data set. So we had a lot of initially we studied with this first data set that basically has 200 speakers, and this is across 12 different Indian languages along with English, of course. Sorry. The second data set is the bigger one. It has roughly 345 speakers, only 5 Indian languages plus English, but per each native language we have minimum 60 speakers. I think Hindi has more, something like 100 speakers. And both the native language and English speech is collected from same speaker. So the data set contains native language, the mother tongue of the person, whether he can read and write his mother tongue. Second language, which is the mostly spoken language, which is different than L1. The regional information, where is the place of the origin, dominantly lived place, etc. And of course, the physical characteristic information. Here we tried to look at height, shoulder size, waist size we wanted to look at, but then we had to drop it due to other issues. Weight, age, and gender. So this is basically the set of languages. In the first data set, we had 10 different languages. 2 minutes per speaker is the set. The second data set, which I told is the bigger data set, we had around 20 to 25 unique sentences, short story sentences, and two common sentences. English, there were some 5 common sentences, some unique sentences, and short story sentences. So, roughly, there are 4 to 5 minutes of data is available per each of the speaker. We have recorded all the four major South Indian languages, Hindi and English for this study. Here, something like 200 male speakers and 120 female speakers. Now, that's basically the number of speakers per region for the two data sets. Here you will see more variability, but there are less number of people. Here, this is the second data set, which is larger, so but it has only limited variability because we only collected 5 different languages. So basically, we use the same kind of techniques and algorithms to evaluate, but this time evaluating for more speaker profiling things like shoulder size, weight, etc. Okay, this is the first data set results. I'll skip this. Let me go to the second data set. And so this is basically the mean prediction, and this is basically the together prediction. So you see that this is improved as compared to the MAE here. And now these are the shoulder is pretty difficult to improve because already it is a very small variability available. So if you say that if you just predict one number, even then the mean square error is something like 2.5 centimeter, which is already small. It is very difficult to improve on this. But other things have been in general improved. So since this is a multilingual data set, we also tried to look at the effect of language. You have English as well as native um, language, so you can try all different combinations. You can train with English data and test with English data. You can train with English data and do a mismatched testing with another language. You can train with the native language and test with the native language. You can train with the native language and test with English. So all those four different combinations we did, and they are more or less around the same performance. It's all around 5, for example, in case of male height prediction. Female height prediction, it's all around 5.6 or something. So basically, the mismatched condition does not change too much. It does not affect the performance too much, which is a good news because you don't want to all these algorithms to fall apart when you have a different language. So, so this is the basic idea about speaker profiling. But we were more looking towards a system where we could. So this was a lot of engineering, right? You tried to look at MFCC features. You somehow tried to summarize it over the entire sentence. You try to look at another features, which is formants. You try to somehow find the percentiles, log percentiles, in fact, harmonics. You try to look at the amplitude, then the frequency, then summarize it over the sentence. So this was a lot of engineering. So we wanted to move from there to building a machine learning system which is more or less automatic. Okay. So we tried to look at deep learning architecture for this purpose. So this is basic deep learning architecture that we used. So we have an input which is having n frames. So you have a speech which may be 1 second or 2 second or 3 second. If it is 1 second, it will have 100 frames. If it is 2 second, it will have 200 frames. So this input to the deep learning network is actually a variable length. So that's the basic idea which we should realize here. So this is a variable length input, but each of the frame will have 60 features. So what we tried to do is we talked about 200 sound classes and finding their probabilities. So that we tried to do it for each of the single frame as such. So each of the single frame will get mapped to 256 different probability values. So that particular part is taken care by this side of the neural network. This is just a neural network. Every time you try to multiply, accumulate into a set of neurons. So there are 256 hidden neurons here, 512 hidden neurons here, back to 256 hidden neurons here. Now you need to do this averaging to find out the f-stats. You need to multiply the input features with those probabilities and find the average. So this is the multiplication block. There is no neural network layer here. It's just a multiplication layer. Just multiply this with each of these values. You get these numbers and you try to do a mean layer over the last axis, which is variable, which is the length of this feature. So you get a mean thing which is 256 cross 60. So that is basically each of the 60 is a spectral average of each of those 256 sound classes. So you try to make it as one single feature vector, this 256 cross 60, and then you try to predict, for example, age or height or things like this. So this is the entire neural network architecture. Now, what we did new in this was we tried to use our previous training to initialize this neural network. So we used to this part to find the posterior probabilities, and we trained this part separately by using the probabilities we already had from our previous model, the Gaussian mixture model. This is just a multiply add layer which didn't have to be trained. But whereas this part, which you predict these numbers from that, this we initialized using our support vector regression weights, which is the algorithm which we have used in the previous work. So we used a support vector regression to initialize these weights. We used our Gaussian mixture model to initialize these weights, and it was noted that without initializing these weights, things just didn't work. So that is the initialization part. Part one was initialized with the of the DNN was initialized with this GMM UBM weights, and the last part was initialized from the support vector regression. And once that is initialized, we train it using all the timid data that we have, and until it converges, it's a standard neural network training. And we actually improved uh, with respect to the previous algorithms. So you can see that the major thing what we improved is the age. The height, we kind of got to this particular result, but didn't really move past the state of the art. But at least for the age, this is the best state of the art system in the literature now. And what is special about this system is, again, this was very robust to duration. Even the same thing here. Even if you go towards shorter segments, the deep neural network is very stable with respect to the duration of the speech. Even with the short duration, like 2 seconds, it is able to predict things very clearly. For example, the left picture is about age. So whether you go until this is the 1 second, the leftmost thing. After 1 second, it increases. So till 1 second, it is almost flat. The lowest part is the DNN thing here. Similarly, even the second picture, the lowest one, the yellow one, is the DNN, and it is the one which gives the lowest error when you reduce the size of the um, speech input data. And this is more like a detailed research. I think I'll skip the slide. So in general, we wanted to do speaker profiling, which I hope it is something which will catch up for many other applications. We used Melkepstrom, Formants, and Harmonics. And those are features which do not require any special sound to be pronounced, as contradiction to today's best research. And we also tested for other physical parameters like weight and shoulder size and other things like that. And some of them were successful. I think weight was successful, not really. Shoulder size, we found that there is very less variation across people. And we looked at this deep neural network which can do all of that at one go. And that is, we verified that with the timid and this our whatever data sets we had collected. And we looked at this initializing thing which made the whole deep neural network work. And that was actually a success. So I think a couple of things which I wanted to tell people, if anybody is planning to work on these things, is one, this data set is public. This data set on the second data set, which has actually more speakers and which has this doesn't have too much of data and it is very difficult to work with. So we decided to release this data set, which is a lot of data. It is almost like 20 hours or something per each of the language, I believe. Anyway, so yeah, not 20 hours per language. I think overall it is something like 52 hours. That's a lot of speech. So this is a publicly available data set, and we will try to help you if you have any difficulties. If you want to start your research with something similar, we would be happy to help you with these data sets and algorithms. Okay. And the second thing is something which we learned about neural networks. The data at the level of at the levels which we see usually, that is For example, Timid is a few hours, or this data set which we collected is a few hours. So those are not really enough for training deep neural networks at these big neural networks. So generally, having a initialization helps them a lot. So that's two things which I wanted to mention at the mention as at the end of the talk. Okay. Thank you. I think we could take a few questions. I would like to stop at this point.
Good afternoon, sir.
Yes, please. Hello.
No.
Hello. Yeah, I can hear you. Go ahead.
Oh, sir, this is Sri Lakshmi from Vijayawada, Andhra Pradesh. Sir, I want to know whether the data set that you mentioned earlier, is that data set can be used for emotion recognition, sir? Speech
See,
recognition.
this is more of a read speech. People have been reading whatever is displayed on the speech. So I don't know if there will be too much of emotions in that. Uh, uh, I really doubt. The second thing is nobody has looked at in that perspective. But if you're looking at the emotion detection, maybe it is better to actually look for data sets that actually has a emotion marked, that is annotated in the data set. So there are a lot of them. There is, for example, one known as IEMO-CAP. That is, there are a couple of challenges which is happening in speech, which is about emotion detection. I think if you register for these things and participate in that, you will get data to train your algorithm and test it. Yeah.
Okay, sir. Thank you, sir.
Sir, one more.
Yeah.
Sir, here you have taken height, weight, and age as the parameters to
Yeah.
evaluate the model. So, how
Yeah.
far the height is going to affect, sir? Because age, as the age grows, the voice of the speaker would be different. In what way height taking it as a parameter would be affecting the system in designing?
So actually, height systems are there for. I mean, I don't think we are the first ones to look at height.
Yes, yes.
Height, the relation people say is your height kind of affect your height of the neck. That's the correlation that people are hypothesizing, because if your neck is longer or shorter, you have that information in your speech, because your neck is part of your vocal tract. This is basically a part of the apparatus which makes your speech. So for example, what I showed as formants, that will, this is basically the resonant frequencies of the tube. So the resonant frequency of the tube will depend on the length of the tube, and that involves your neck height.
Height of the neck.
Yeah, basically, and that people say that is in general correlated with your height. Of course, knowing your neck height won't, somebody won't be able to exactly tell you your height, but that can give you a approximation, and this is what is the relation that people play.
Okay, sir. And one more thing, sir. Do we have, when we are computing using these parameters and time domain analysis, so where actually we are going to find a major difference between the harmonics and the formant, sir?
Okay. Can you repeat the question? What's the difference in the sense?
Between harmonics and the base frequency. Harmonics or
Base
formants.
frequency is really the base frequency. Can you see the slide now?
Yes,
Or
sir. We are able to see it. I'm
okay,
able to see it.
okay, fine. So harmonic is this fine lines. If you see, okay, there are very fine lines in
Yes,
horizontally. That's harmonics.
yes, sir.
Formants is this thick things which is flowing across different frames. So those are two different things basically.
Okay, sir. Sir, for any analysis, to what level of the extents of format should we consider? Just F1 or F2 is okay, or should we consider all the formats that is available in the spectrogram?
So we were talking about harmonics and formant. So basically, if you look at here, there is one formant going here, one formant going high, another formant coming low, and another formant going flat. There are only like 4 or 5 formants here. But if you look at the fine structure, let me probably see if I can zoom it. Are you able to see a zoomed version?
Yes, sir. Yes, sir.
Yeah, okay. So here, for example, let me take the towards the end part. You will, or let me take here. So here you will see one formant going here, two formant going here, three formant which is like this, fourth formant like this, fifth formant which is really small.
Yes, sir.
That's 5 formats. But if you look at harmonics, you will see a lot of fine lines going horizontally. This is all the
Yes.
spectra. So those fine lines are basically harmonics, and those coarse things are harmonics. Okay, so the harmonics are related from your how your vocal tract looks like, the shape of the vocal tract, length of the vocal tract, all those things. And these harmonics are depending on how your vocal cords in the throat vibrate. One is about the vibration, and one is about how that is coming from the coming through the whole vocal apparatus. To give you an analogy, let's say you are looking at a flute, right? So you blow it and you close some of the holes, and that's what gets you the sound. Now, the fact that you blow it is the excitation. You blow and create a sound there. You create some kind of a vibration in the air. Now, how that sound gets produced is because of your uh, what you close and what you open, basically the tube. So those are two different things. One is about how you give the energy through the vibration, that is what makes this harmonics, and one is how you change your shape of your tongue, vocal tract, everything. That's the second thing. So if you look at that, these harmonics are constant across the time, they don't change much.
Oh,
Your but your formants do change a lot when you speak.
yes,
That
yes.
depends on the sound. Basically, that depends on the sound, and harmonics depends on your throat. Your throat don't change much. You can change your pitch, but not too much.
Yes, sir. Yes, sir. Okay, got it, sir. Sir, but one question is, how many formats should we consider? So, should we consider all the available formats that
We
are?
considered like four of them. F one, two, three, four. Basically,
Okay.
these things: one, two, three, and four. The fifth one is really not there many times.
Sir, to have these values of these formats or the basic fundamental frequencies, so can we use this Pratt software and take the min and max values of each formats, and then we can use those values for the computation, sir?
Fundamental frequency, you can compute it from Pratt. I don't know if F1, F2, F3, F4, I don't know if you can compute it from Pratt. But if you are,
Which tool you are going to suggest us, sir?
we used Python only, but there were some a linear prediction function which was available. So if you look up a linear prediction, you can see how to find the poles of the transfer function, and basically those are the frequencies. You convert that pole into a frequency, you will get
How is
the
sir?
transfer function. That's what it is. So it's two, three, maybe 4, 5 lines of Python code. Yeah.
Okay. Okay. So this we have to convert into frequencies. The poles has to be
Basically, we
converted
need
into
to, yeah, yeah. Yeah, we have to find the frequency basically. We have to find this y-axis frequency values.
Okay. Okay. Sir,
Harmonics, it is easy to find because you can look at the spectrum and try to look at these local peaks. That will be harmonics. So this is a harmonic, first harmonic, second harmonic, third harmonic, fourth harmonic, fifth harmonic, etc.
Sir, and the frequency between two harmonics, you have written it as 230 hertz or
That's the
160
pitch.
hertz.
That's the pitch. Yeah.
Okay,
Let's
even
say
that.
F0. That's F0.
Oh, F0. Oh, F naught.
Yeah,
Okay, sir.
F
Okay,
naught.
okay.
Yeah, yeah.
Sir, could we reassign like F naught or F1, F2? Like what we are assigning F naught is pitch. So
Yeah,
F1 is what is that? Like, can we correlate with can we name with taxonomy?
I think you can
Like
name it
pitch or
whatever way you want. I think this is F0. Basically, the spacing between the harmonics is going to be your F0.
okay, sir. So always the more speaker data is good or less speaker data with many variabilities are good, sir.
I think
Because
always more speaker data is good. No doubt about it.
okay, so the way that in mean absolute error, mean
Okay.
square error, sir, you have used mean absolute error also.
Mm-hmm.
So in the mean absolute error, can we apply for all the formats of this?
No, that's the measure. When you predict it, you use mean absolute error to figure out how much error you have, how much error in height you have. So we said
Okay,
5.7, 5.7 centimeter on a root mean square sense,
okay, sir.
or 5.7 centimeter on a mean absolute error sense. So you find all the errors of all the speakers that you did and
Hmm.
find their absolute value and find the mean. It is 5.7. That is what it means.
Okay. So, but these to be used together, sir. Mean absolute error and mean square error need not be no, sir.
It
I
is
can use
any.
any one error
Generally,
method.
people use one error. So what we find is, so if there are large errors, this will reflect it. So let's say you are doing good with most of the speakers, but if there are some speakers which is especially doing bad, then this will
RMSE is
catch
most
it.
probably seen and applied, sir.
And this will actually give you an idea about most of the speakers. But if there are some speakers which are especially doing bad, MAE will not catch it. So that's the difference which we found.
Okay. Okay, sir. Thank you, sir. Thank you.
Thank you.
Participants, if you are having any clarifications or doubts, you can, sir, can take up one or two questions. If you have any doubts, you can ask.
Hello.
No doubts?
Hello,
Yeah, please.
sir. Actually, can we do the speaker direction for the Indian languages?
We should be able to do speaker diarization for Indian languages, but mm, I'm afraid that we don't have enough data for it. We don't have any data for it. Basically, speaker diarization is done on conversations, right? There are two or more people speaking together. I am not aware of any data set at this point in Indian languages where we can do it. So, yeah, if you are planning to do it, maybe the first thing you need to do is collect data.
Okay, sir. Okay. Thank you very
And
much.
probably, if you are really planning to do it seriously, maybe try to record a very small set of data, only a few speakers, and try to see if the existing algorithms work there. It might work because most of the speaker diarization algorithms, they don't use the language information. They only worry about the speaker models.
Okay, sir.
Yeah. Thank you.
Okay. Thank you so much.
Sir, lastly, sir, sir, if any data set you are aware for pathological speech processing, sir?
Pathological speech processing, there is a whole group working in India. I think, Professor Prasanna, Professor Mahadev Prasanna,
Yes,
Triple IT Dharwad director.
yes, sir, we know that. We know him,
Yeah,
but
he is working with this one. And of course, the data is actually from Mysore, if you know it. You have this
Ayush,
Aisha, India Institute for
do we
Speech
have
and
any
Hearing.
open repository, something like Timet,
I don't think the data is open since it's a pathology data. It's probably a sensitive data. They may not be able to release it in open source. But I think if you are planning to work with them, you can talk to them and you will be able to access the data.
Okay, sir.
but probably one may not be able to publish that data just like that. I think if you talk to the doctors, you will know.
Okay, sir. Thank you,
Yeah,
sir.
yeah.
So participants, if you are not having any doubts, so we can conclude the session. So I thank Deepu sir for sharing this knowledge with us and also gave more insight on how time variant factors are going to play a major role and how actually the error computations and the analysis of the basic parameters in estimating the speaker's mm, in estimating speaker profiling or predicting the data for the different using different parameters. So it was a very nice session to hear from you, sir. So we thank on behalf of the college and the department, we thank you for accepting our invitation and delivering a talk on this FDD, sir. So thank you very much, sir. If any things are required, so we'll keep in touch with you and we may contact you, no, sir.
Okay, sure. Thank you.
Okay, sir.
Thanks a lot. Have a nice day. Bye.
Yeah, sir. Thank you. Sir, one more thing.
Yes.
You should share the PPT, sir.
I'll email you the PPT.
Yes, sir. Yes, sir.
Okay. Thank you.
Thank you, sir. Thank you once again, sir.
Bye.
Bye, sir. Thank you all the participants. We are going to conclude the today's session. So we are going to end the meet. Tomorrow we shall end for the day. Tomorrow we are going to have our second day session opening with the digital model representation of the speech signals. So you are supposed to log in by 9:15. Link are we sending? We will be sending a link. Hope that's fine. Thank you once again for all the participants for joining us for the day and making a success of the today's program. Thank you one and all.